welcome back to Nimble Tutoring. Today we're going to be covering the topics of rational approximation and Taylor series. And you might not have heard rational approximation used in this class, but you'll see how it becomes relevant just from a couple examples. So in this video, it is purely conceptual. There will not be any problems in this video. We're going to save the problems for a later video since we have a lot to talk about in this. So we're going to start off by talking about how to use polynomials to approximate non-polynomial functions. And we're going to show these things called Maclaurin series for the functions sine, cosine, and e to the x. Then we're going to define a Taylor series. And finally, we're going to look at the Lagrange Error Bound Test. So let's go ahead and jump right into it and talk about rational approximation. Alright, to start off explaining how to do Taylor-Maclaurin series and all that jazz, we're going to start with something a little bit different. We're going to take this function e to the x, and we're going to try to write a polynomial that approximates what it looks like. And for reference, we're going to use this point right here at 0, 1. And we're going to use that point to write a polynomial that estimates it. So to start with, let's write a constant term polynomial. So no x in the polynomial at all, just a constant. So if we're approximating it at x equals 0, what constant should we put in? Well, the answer would be 1, since the only data we really have is right here at this point. We have that the value is 1. So we draw this graph y equals 1, and you can see this is a really bad approximation of the graph. But to be fair, we have no x in there, it's a 0-degree polynomial, so it can't be that good of an approximation. Let's try a first-degree polynomial. So we know that the constant term is going to be 1. What's the x term going to be? Well, what we want to do is we want this function here to have the same slope or derivative at this point. And remember, we have to put it at this point, because this point is all we're using for reference. So we have the derivative at this point is 1. Because derivative of e to the x is e to the x, and e to the 0 is 1. So what we do is we want the derivative of our approximation polynomial to also be 1. So we have derivative of the first term, and we call the first term t1. T for term. So we want the derivative of the first term to be 1, and then so we can integrate both sides. And we have that the first term is equal to the integral of 1 with respect to x, and we have x over 1. And you might think that the over 1 isn't super important, and really isn't, but you'll see why I'm putting that there later. So we find that the first term is x over 1, and then we add that to the constant term, which is 1, and we get this function, 1 plus x over 1. And you can see, it's still not a very good approximation of this curve, since, you know, it goes down to infinity over here, this curve grows much faster. But it's getting closer. It's a lot better than that previous one. Alright, so now let's try to do a quadratic polynomial that approximates this. Well, what's the second term going to be? Well, for that, we're going to find the second derivative of this function. And we know the second derivative is going to be 1 again. Because every derivative of e to the x is e to the x, and e to the 0 is always 1. So what we want to do now is, because the second derivative of t2 of x, t2 being the second term, is 1, we have to take the integral twice to figure out what the second term is. So we take a double integral of the second term, or to get the second term. So we have integral of 1 with respect to x. And we get x squared over 1 times 2. Where does the 1 times 2 come from? Well, the first time we did it, we get x over 1, because x is the first power. The second time we did it, since x is the second power, we have to divide by 2. That's our integration rules. And if you think about it, if you take the derivative of this twice, first you multiply by 2 and reduce the power to 1, and that cancels this 2. And then you multiply by 1 and reduce the power to 0, which cancels this 1. And we're just left with x to 0, which is 1. So you can see these numbers at the bottom just get bigger and bigger, and are multiplied in order. So let's see how our polynomial looks like now. And you can see it's getting closer to this curve. It's still got a long way to go, but it's getting closer. Right? So now let's add a third term. And at this point, I'm sure you can tell where this is going. We're going to keep increasing this exponent by 1, and we're going to keep multiplying by the new exponent. So this is what the third polynomial looks like. And you can see right over here that we have x cubed over 1 times 2 times 3. And in total, what we get is, if we take this to infinity terms, which we need infinitely many terms to approximate this curve, so it's not actually a polynomial function. It's an exponential. But if we take infinitely many terms to approximate it, we'll get so close that we'll actually get the right answer. And this is what our function ends up being. We get sum from n equals 0 to infinity of x to the n over n factorial. And if you haven't seen n factorial before, It means multiply all the numbers from 1 to n, and then 0 factorial is just 1. So, for instance, let's say we want to find this from n equals 0 to 5. We have x to the 0, which is 1 over 1, so 1. Then we have 1 equals n, so we have x to the 1 over 1, so x. Then we have 2, we have x squared over 2 factorial, which is x squared over 2. And the third term, x cubed over 6. The fourth term is x to the 4th over 24. And the fifth term is x to the 5th over 120. And so you can see the denominator is growing very rapidly, whereas the numerator just keeps expanding in powers. And as we make more of these polynomials, as you can see with these graphs I've been drawing, we get closer and closer to the actual curve e to the x. So this is what's called a Maclaurin polynomial. It's trying to approximate this green curve, e to the x, at x equals 0 specifically, and you get this really nice approximation. And if you carry it out to infinity, it's called a Maclaurin series, because this is a series. So this entire unit is about using these approximation polynomials to try and figure out the value of a function on a curve, using just a polynomial. Because here's why this is useful. Let's say we want to evaluate the value e to the power of, let's say, pi. And you might not know how to do that with paper and pencil. And in fact, I don't know if there is a good way to do this with paper and pencil. But what you can do is, you can take this polynomial, and you can get a pretty good approximation by doing, like, say, 5 or 6 terms. If you want to write a computer program to do it, you can even take it to like 100 terms, or 1,000 terms. And then you'll be really close. Then what you do is you can just plug in x equals pi to this polynomial, and you can easily evaluate them by hand, because pi to the n is an actual value you can calculate, although maybe not very efficiently either. And although it would take a while to evaluate 1,000 terms of this polynomial, it's a lot easier to do that. And we're going to show another example of it right here. This is an even better one. So this function here, you'll recognize is sine of x. Right? Pretty simple. So now, suppose you want to calculate the value of sine of 1 radian. Well, you can't really do that other than plugging it into your calculator. And you might be wondering, well, how does my calculator do it? How do they know what sine of 1 is? And the answer is they also probably use this polynomial approximation method. So what you do is, you start out by just evaluating the curve at x equals 0, and you get 0. This is your bad approximation. Next up, you evaluate it with one derivative, degree 1 polynomial, and you get this curve, which has a slope of 1, it's just y equals x. So now, you'll notice over here that I skip the second term, and I go straight to the x cubed term. That's because the second derivative of sine at 0 is just 0. And then since anything times 0 is 0, that term just cancels out. So I'm skipping straight ahead to the third term. And also, instead of writing out the terms, I'm just writing f triple prime of 0. And sometimes you replace the 3 primes with a 3 in parentheses, just for notation, because it gets, as you get to more and more derivatives, it gets tedious to write out all those prime symbols, and it can be really hard to count them. Like, say you want to take the 17th derivative of a function, just to take a really exaggerated example. No one wants to count out 17 prime symbols to figure out what you're talking about. So, we have the x cubed over 3 factorial, and then f triple prime of 0, our third derivative of 0, is going to be negative 1 in this case. And then, what we do is, we take this curve and we graph it, and you can see it's getting even closer to sine. Like, look how close this is for this interval right here. It looks quite similar. And then we can take this to the 5th degree. Again, we're skipping the 4th degree because fourth derivative of sine at 0 is 0. And we get this polynomial. And look how close this is. It like approximates almost an entire period of sine. Or I guess half a period. So this is a really good approximation. And if you carry this out for a couple more terms, you'll get a near perfect approximation of 1 period of sine. So again, why is this useful? Well, we can plug in the first couple terms and get a really good approximation. Again, this is our polynomial. This is our infinite series for it. And it looks a bit different than the other series. You're wondering, where does 2n plus 1 come from? That's because I've simplified this a little bit. We know that the derivatives of sine at 0 alternate 1, 0, negative 1, 0, 1, 0, negative 1, 0 forever. And I would like you to verify this for yourself if you don't understand why this is immediately. So, like, take the first couple derivatives of sine, plug in 0, see where it gets you. So the 2n plus 1 means that every n you skip ahead by 2, So it only takes the odd values. So it skips ahead over all the even ones, which will give you 0, and these terms don't matter. And same with the denominator here, since we're only using the odd terms up here, we have to only use the odd terms in the denominator. And then -1 to the n is because sign is alternating every 2 terms, so it goes 1, -1, 1, -1. And again, please, I would love it if you could verify for yourself, because you always get more out of learning if you learn it yourself instead of just having someone else tell you what's right. And so, again, if you want to estimate sine of 1 radian, you take the first, say, 4 terms of this polynomial, and then you plug in 1. So you have, say, 0 plus 1 minus 1 over 6 plus 1 over 20. And that's a pretty good approximation of sine of 1. So that's an easy fraction calculation that you can easily do by hand even. But it gives you a really close approximation to sine of 1, and it's like accurate to 3 decimal places at least. If you carry it out to more terms, you can get it accurate to your calculator screen. I remember you can, if you know a bit of coding, I'd make it a good challenge to write a program that calculates the first 10 or so terms of sine, and then can find the sine of any angle. But I'll leave that as a challenge to any of you coding nerds out there. So anyway, here's another example. We have cosine. And again, for cosine, we're going to skip the odd terms instead of the even terms. Because the derivative of cosine is negative sine. And negative sine of 0 is 0. So here are the first couple polynomials. You can see they get closer and closer to a good approximation. Here's the 6-degree one. We use 4 terms. And it's 6 degree not because of the number of terms, because there are only 4 terms here. And it's a bit cut off, I'm sorry about that. But the reason it's 6 degree is because you have an x to the 6 in there. That's the highest degree term. And this is your infinite series for it. Again, I would like you to verify that this works similarly to how sine works, but it's just because of how cosine derivatives work. But yeah, so again, if you wanted to evaluate, say, cosine of 1, you plug it into your polynomial. So now here's a weird one. We have ln of x, and we want to approximate this with a polynomial. So we go at x equals 0, and we try to take our value there, and we're stuck. Because ln of 0 doesn't actually exist. So how do we approximate this? Well, the answer is we have to approximate it at an x value other than 0. So we approximate it at x equals 1, say, okay? So we draw our constant term here. It's a terrible approximation, as usual. And now we take our f prime of 1, and we plug that into our function. But we can't multiply it by x, because we're not centered at x equals 0 anymore. We're not approximating from x equals 0. So if you plug in 1 to this function, f of 1 plus f prime of 1 times x, you'll actually mess it up, because f prime of 1 times x is not the same value when x equals 1. When x equals 0, it just cancels out. But when x equals 1, it actually adds to the term and messes it up. So we have to change x to x minus 1, so that we're not changing the value at x equals 1. Because it's already correct here, that's what the constant term did. So we don't want to change the value at x equals 1. So we change this to x minus 1 instead of x. And behold, it still matches right at this point, because plugging in 1 to this entire term becomes 0. So now again, we go to the x squared term, but we replace every instance of x with x minus 1, and we get this parabola. And then finally we do this cubic, and you can see the approximation is getting better and better, even though we didn't start at x equals 0, we started at x equals 1. So all we have to do is change all instances of x to x minus 1, and this is called a Taylor polynomial instead of Maclaurin. Taylor is like the more generalized version of Maclaurin, or more accurately, Maclaurin is a specified version of Taylor, since Taylor came first, I believe. But basically how that works is, you do the same thing as you would do for Maclaurin polynomials, except you pick some center that you want to do it around. In this case we picked 1, just because 1 is easy, because ln of 1 is 0. And then we change all instances of x to x minus c, where c is the value we picked, so in this case it's x minus 1. And it's called c because c is what's called the center of our approximation, because we're building our polynomial around that point. And it will always be perfectly accurate right there. So here's our infinite sum for log, or ln rather. And I didn't write it out fully this time because I don't want to evaluate all the derivatives of ln. But basically we take the nth derivative of 1, and then we do x minus 1 to the n all over n factorial. And this is the general formula. If you change 1 to c, and then you let f of x be any function you want, this is the general formula for a Taylor polynomial. So this 1 means it's centered at 1. If you change this to c, it can be centered anywhere you want. If you let c equal 0, then this just becomes x to the n. This is the exact Maclaurin formula we had earlier. So this is the general formula for a Taylor series. So yeah, Taylor series is just approximating a polynomial, or approximating a function using a polynomial. And the whole point is it makes things easier to estimate. Like, remember right here, say you want to know ln of 2. Well, you can just look at this polynomial, plug in the first couple terms, and get it. So this is really all about estimating the values of functions that are very hard to estimate normally, like sine, cosine, e to the x, ln, anything that's not a polynomial, really. It's turning it into a polynomial to make it easier to estimate. And this is actually how your calculator evaluates sine and cosine and things like that. So it's pretty cool. And next I'm going to quickly talk about a useful tool called the Maclaurin Error Bound Test, or the Lagrange Error Bound Test, rather. And that tells you how close your approximation at, say, ln of 2 or sine of 1. It tells you how close your approximation is to the actual value, because you can't actually evaluate infinitely many terms. You'd grow tired pretty fast. But if you evaluate the first couple terms, you come pretty close. So the Lagrange Error Bound Test, it tells you exactly how close you are, and I'm going to go over that in a second. Alright, so our last topic for this video is the Lagrange Error Bound Test. And what this is useful for is, all these polynomial approximations we've been making are great and all, but they are just approximations, they're not exact. And unless we want to go to all the infinitely many terms and sum them all, we're not going to get a perfect approximation. So, what we need to do is figure out exactly how accurate our approximations are, so that when we use them for real-world values, like say, we need to know the value of sine of 2 for some machine part. Well, we need to specify how accurate this needs to be. Like, say, the machine part has to be accurate to 6 decimal places. Well, we need to figure out how many terms of our polynomial approximation we need to calculate, so that we're accurate to 6 decimal places. And for that, we need to know our error, which is the difference between our approximation and the actual value of the function. So, how accurate are these? We can use the Lagrange Error Bound Test, which is based on Taylor's theorem. And Taylor's theorem says, when you're estimating f of x using an approximation centered at the value c, and you'll remember the center of your approximation is the point you're building the polynomial around. So for Maclaurin polynomials, c is 0. And for Taylor polynomials, like we had for ln, the center of that was 1 because we had x minus 1 in all our terms, and we built it around the derivatives and the value at the point x equals 1. So anyway, given the value c and x, we can say that there exists some z between c and x, such that the error of our approximation of f of x is less than or equal to this value. And f to the n plus 1 power is just a fancy way of writing the n plus 1's derivative of f. So the n plus 1's derivative of f at z times x minus c to the n plus 1, all over n plus 1 factorial. And if this looks familiar to you, that's because this is the next term in our polynomial approximation. So, since we're approximating to the nth degree term, this is the n plus 1th degree term in our polynomial approximation, except that we change the n plus 1th derivative. Instead of approximating it at c, we take it at z. And this is nice and all, but the issue is, we don't actually know the value of z. So we can't figure out our error because we just know that there will exist some z, or this is true, but we don't know the exact value of z. However, most of the time we don't care what the error is exactly. We just need to know the maximum value the error can be. Because if we calculate that the error is, say, 1 over a million, and the error turns out to actually be 1 over a billion, it doesn't really matter because we just end up being closer than we thought we were, and that's just a happy surprise. So all we need to do is maximize this value, which means that we just pick a value of z that maximizes the n plus 1's derivative of f at z, and that will be the maximal error that we'll have. So to calculate this, we maximize the n plus 1's derivative of z on the interval cx, and we multiply by the term on the right, and that gives us the maximal error that our approximation will be. So that means our approximation plus or minus this error, the actual value of the function will be within this interval. So that lets you say with pretty good certainty how close your approximation is to the actual value. And just evaluating like the first 6 or so terms, you can see using this test that your error will be like, frequently, it'll be in the 1/1,000,000 range. And this is a pretty good estimate. For all real-world purposes, this is good enough. So that's all we have for you today in this video. There'll be more coming soon on other topics, and we'll have some actual problems coming up. But anyway, thank you so much for watching our video. If you want to contact us to ask any questions about this or suggest a future video, you can email us at timberwolftutoring@gmail.com or find us on Instagram at Timberwolf Tutoring. And remember, we also have a new Google site where we're putting all our videos, and it's more organized than the YouTube channel is. So if you want to check out some of our other videos, please head over to the Google site. It's timberwolftutoring.org. And that's all we have for you this time. This is Robin and the rest of the Timberwolf Tutoring crew signing off. Until next time, have a great day.